Okay, good morning, everyone. So, we are doing some more number systems stuff. Particularly, this video is going to be about hexadecimal. So, um, the only way it really makes sense is to compare it to some of the other number systems. So, let's start with our own, the decimal or base 10 number system. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. We get the picture. We know what's going on. 12, 13, 14, 15, 16, 17, so on and so on. The number system, we grew up with, the one we all know and love. And last time we talked about this, we talked about octal numbers. Octal numbers. So octal is base 8. So what that means is we start counting. It kind of looks normal. 0, 1, 2, 3, 4, 5, 6, 7. But once we get to 8, we go to 10 instead. Since octal is base 8, there's 8 digits, 0 through 7. Once you go to 7, you jump right to 10, our first double digit number. And then count kind of like 1, 1, 1, 1, 11, then 12, and then 13. Well, it should be, let's do it like 12, 13, 14, 15, 16, 17, 20, 21. Again, we skipped to 20 because in octal, it's just no eights or nines. I haven't made a video on this, but binary, base 2, only got 2 digits. 0 and 1. So like we go 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. I don't know. It's not matching up at all with the other charts, so just, But you can just count it out and see what I'm, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, and so on and so on. Base 2, we only have 2 digits. So what makes hexadecimal really nifty? Let me do this. Just because I need to make a nice, neat chart so we can compare all our numbers accurately. It's not going to be great, but it's going to be all right. Can I move this? Yes, cool. All right. So what makes hexadecimal particularly cool and unique is that it's our first number system that the first one you're probably dealing with that is a base that's above like 10. So like binary, octal is a base that's like 8 and 2 respectively, or the quaternaries, which is base 4. These number systems we've been kind of seeing and dealing with have all been like below base 10. So what happens when we have a number system that, like in hexadecimal's case, is above 10? It's 16, base 16. What the hell do you do? Oh, whoops, sorry. What do you do in that circumstance? This is taking forever. So yeah, hexadecimal is base 16. If you think of like a hexagon, you get 6. And then hexadecimal, decimal, is Latin for 10. So 6 and 10 is 16. That's where you get the name from. So, all right, we got hexadecimal. Hexadecimal. Okay, so base 16. Base 16. So you start counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13. What? Whoa. My bad. No, not 10. So why wouldn't I go to 10? Because we're in base 16. I need 16 unique digits. Before I start jumping to double digit numbers, I have to fill up 16 single digit values. Starting with 0 to 9, we have 10 digits. So how do I make up the rest? Well, in hexa, you just say, all right, you put A, B, C, D, E, 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 F, and then 10. So we ran out of the typical digits at 9, so we just use letters in the alphabet starting with A through F to make up for the rest. So if you count it out, right, we from 0 to 9, that's 10 digits, and then A is 11. A is 10 in our number system, but I mean A is the 11th digit, B is the 12th digit, C is the 13th digit, D is the 14th digit, E is the 15th digit, and F is the 16th digit. Remember, that's including 0. So, but in like our number sense, like A is equal to 10 in our number system, B is equal to 11 in our number system, D is equal to 13 in our number system, so on and so on. And just like how it worked with octal, where in octal, 10 and 8 are the same. In hexadecimal, since we're in base 16, hexa's 10 is equal to our 16. So we only jump to the 1, 0 to 10 after counting up to 15. So a little freaky, a little weird to get your head around at first, but I promise it's really not that bad. Let's try out a problem. So we have this hexadecimal number. What does it look like in our number system? So we have 2 ED. Well, just like all the numbers, it's like all numbers are kind of like base 10 in their own number system is how I like to think about it. So for example, like what I mean by that is, like if I'm breaking this down, we have D times 10 to the 0, but we're still in base 16, hexa. Then I have E times 10 to the first power in base 16. And then plus 2 times 10 squared in base 16. That's what I mean by like every number is base 16 within its own number system. I mean, every number is base 10 within its own number system. But the change happens when we change it to our number system. So we know that since hexa is base 16, I'm going to swap out the 10s for 16s. So 2 times 16 squared. 16 squared. Because this is our jump to base 10 for our conversion. Plus E. Well, all right, what's going on with that? Well, if we look back, E in our number system is equivalent to 14. So I'm going to swap out the E with a 14. and then swap out the 10 with a 16 to the first power. Plus D, well, you can kind of, you can just count backwards. It's going to be 13 in our number system times 16 to the 0th power base 10. Okay. So from there, you just crunch out the numbers. So 16 squared, 256, plus 14 times 16 plus 3 times 16 to the 0 is just 1. And if you run all these, if you multiply this out and add the sum, you should get 749. And that's our base 10 value for what in hexadecimal is 2ED. So that's how you do a basic conversion into decimal. It's kind of a pain, to be honest. Like, all the number crunching you got to do, but it is what it is. So what if I have a number in decimal and I want to convert it to hexadecimal? Well, we're going to take, all right, we have 333 base 10. So you take that number, 333, and we're going to divide it with 16, long division style. So how many times does 16 go into 33? Twice, because you get 32. Subtract, you get 1, carry the 3 down, 13. 16 goes into 13 0 times. So our remainder is 13. Remainder of 13. Okay. From there, we take our quotient of 20 and we're going to divide that by 16. So 20 divided by 16. Well, 16 goes into 20 once. Subtract. We have a leftover 4 as our remainder. And then, again, take that quotient and divide it with 16. So the last quotient was 1. We have to divide 16 by 1, which, well, it goes in 0 times. And so we have a remainder of 1 left over. And then once you do that, you are just write out the remainders, like in the, so what I mean is, like, the way you would write out the number is take the last remainder we worked with, the 1, as the leading digit. And then the next one is 4. And then the next one is 13. But if you can recall, 13 in hexadecimal is D. So I'm not going to put the 13 down. I'm going to put a D like that. So 14 or 14D in base 16 is equal to 333 in base 10. That's how you do the conversion to from decimal to hexadecimal. Basically, you just divide by 16 over and over again, and replacing the quotient, each time, until your quotient is 0. And then once you're at 0, you stop, and then the digits are just your remainders in, like, reverse order, basically. So hopefully that makes sense. I'll probably do another video on this, video or two, to really drive the point and talk about, some of the uses of hexadecimal. Like, why would we need to deal with this? It seems really weird. Oh, it is useful. Computers like it. And one point I'll make a video going over that. So stay tuned.